Hello and welcome to Introduction to Nanoscience and Technology. My name is Mike Escuti, and today I want to look a little closer at the photoelectric effect so that we can be really clear on how we know what it teaches us about what's going on inside atoms and how electrons interact within the atom to hold on to energy. Now, let's review what we know very briefly about photons, because photons are really essential to this story. So photons and electromagnetic waves. All right, so first of all, I want you to realize that photons are a kind of energy currency. So I think you should think of photons as the dollars and cents of what happens to energy. And as what we'll see is that, that atoms can gain energy from photons and can give off energy in the form of photons. All right, so thinking, as your textbook says, thinking of photons as a kind of energy currency is really helpful here. All right, but what else do we know about photons and electromagnetic waves? Well, especially we know about EM waves. They have certain properties. One of the key things is that they have an electric field and a magnetic field, and these are interacting together to propagate the photon or to propagate the energy that is contained in the electromagnetic wave. In addition, we know that electromagnetic waves and photons can travel in a vacuum. And that's a really special thing because almost nothing else, no other kind of waves can travel in a vacuum. If you think about it, you know, a sound wave has to travel in a medium like air, and an ocean wave has to travel in a fluid, and so EM waves can travel in a vacuum. Keep that in mind, as well as in other media. EM waves have a maximum speed, which is often given the variable c, as you probably know, and we can say that this is 3 × 10⁸ meters per second, or there's various other ways to express that in different units. And then lastly, we know that this speed of a wave, whatever it happens to be, is equal to the frequency times its wavelength. Right? So this is the frequency and its wavelength. Let me add a little color here for highlight purposes. And then this is the speed of the wave. All right. That is what you probably have known from prior classes or perhaps from reading the textbook. But what else do we know that's really important about photons? There's one other thing I'd like to bring up, and that is the momentum. And that is that, of course, this is the momentum of a photon, or in fact, of an electron. Is actually the same thing. It's the same expression. So let's use this same expression. It's true, as it turns out, for pretty much all particles. So the momentum, P, is equal to Planck's constant, h, divided by the wavelength. And this is true even for large particles. And this is a very old equation. It's about 100 years old, and it describes both photons and electrons. All righty. So let's keep going and walk toward the photoelectric effect a little bit more. All right, so energy in atoms as it relates to photons. Let's think about this just a little bit and make some comments. Now, the first thing to remember from our prior lectures is that atoms gain or lose energy as electrons make transitions between different quantum states. And we're going to draw a picture of this, but let's write it down. So atoms gain or lose energy as electrons transition between different quantum states. Another way to think of this is that as an electron changes its orbital, it's going to transition between quantum states. Its principal quantum number is going to change, and therefore it's going to gain or lose energy. But the second really important thing is a photon is either absorbed or emitted during these transitions. All right, so let's draw what this looks like with a simple cartoon. Now remember, we do not think of atoms as having a planet around a star kind of reality, but because it's hard to draw three-dimensional orbitals, I'm still going to use some of this this kind of cartoonish illustration because it's the best I can do in here in our notes, and in fact it's good enough, I think. So if we have a ground state of something like n is 1, and this is just a picture of an atom, and then this is n is 2, n is 3, and for example n is 4, and these represent the orbitals. And these are the orbitals available to an electron. And if we have an electron, let's say he's here like this, and he goes from a quantum number or an orbital n is 2, and it goes into n is 3 state, then it has raised its orbital, and as we'll see in a moment, that means it's raised its energy. And the only way that that can happen is if a photon is added in this atom, is added to give the atom the energy that it needs to raise up. Now in solids, not just an isolated atom, in solids there are other ways to give the energy to the electron, but at least in this discussion we're just going to limit it to atoms and photons and isolated atoms. This is pretty much the limit. All right, so this is a situation that is going on whenever we have an energy change in an atom. Photon is being added or it's being lost. I guess we can draw also an electron in a higher orbital or higher energy state, and then having it lose its energy going from n is 4 state, or even down to the ground state of n is 1. All right, and so in this case, a photon is going to be emitted, right? And energy of the electron is going to be lost, or of the atom is going to be lost, and it's going to be put into the photon that's going to leave the atom.